değerli katılımcılar, oradan sonraki seçimimiz var. Öncelikle hoş geldiniz. Biliyorsunuz bugün Halkın Uluslararası Kaynak Konferansı açılışı yaptık sabahki programda. Ondan sonraki oturumda da iki salonda yapılıyor. Bizim şu anki bulunduğumuz TURKUAZ salonunda 5 konuşmacımız var. Bir tanesi davetli konuşmacımız. Çok güzel. Konusunu şöyle okuyacak olursam, Moment of Couple Epoxy Accession by Laser Surface Modification. Anons yapabilirsiniz arkadaşlar. Arkadaşlar kapısı. Bu konferansın düzenlenmesinde emeği geçen arkadaşlara öncelikle ben de teşekkür ediyorum. Ve bana bu görev verdikleri için de ayrıyeten teşekkür ediyorum. Özellikle Kaynak Derneği Başkanımız Profesör ve buradaki sorumlu hocamız Ersin Balcı'nın emeklerine sağlık. Öğrenci arkadaşlarımın organizasyonda görev alan bütün arkadaşlarım. Hepsine hayra edin. Teşekkür ederek bu oturumu açmak istiyorum. Tabii ki katılımcımız yabancı olduğu için kısa bir hoş geldin. Şu an kendisi bizi biliyor mu? Henüz değil herhalde.
Hello, can you hear me?
Sakal yazıyoruz. Şey değil mi?
Hello, can you hear me?
Hi. Hello. Good afternoon, ladies and gentlemen. Today our afternoon sessions are going to open and we are starting now. In this section, we have an invited speaker from Portugal, who is Professor Luis Alberto, and I think he is now online, and he is going to speak about improvement of copper epoxy by laser surface modification. Ladies and gentlemen, say to Professor hello. Hello, Professor Luis Alberto. Can you hear me, please? We have invited speaker from Portugal, who is Professor Luis Alberto, and I think he is now online, and he is going to speak about improvement of copper epoxy by laser surface modification. Ladies and gentlemen, say Professor hello. Hello, Professor Luis Alberto. Can you hear me, please? We have invited speaker from Portugal, who is Professor Luis Alberto, and I think he is now online, and he is going to speak about improvement of copper.
hocam. Geç gidiyorsun.
Hello, Professor.
Hello? Can you hear me?
Gecikmeli gidiyor hocam.
Yes, can you hear me, please? Hello? Can you see the slides and can you hear me?
So, welcome to our International Welding Technology Conference, 6th Welding Technology Conference, and we are very happy to see you as an invited speaker. I am talking on behalf of also Professor Adem Kurt. We all listening you from the TURKUAZ Salon in İskenderun Technical University. Thank you joining us, and just I'd like to announce you now and your work, please.
Hello. Hello to everybody. I would like just thank the organizer for the conference to giving me the opportunity to share with you our work in improvement of copper epoxy addition by laser surface modification. First, I'm going to try to show you which is the problem we want to solve, which was the protocol we have in use to fabricate the joints, which are the results we have obtained, and which are the main conclusions of this project.
Bilgisayarın sesinden mi?
Okay. So the problem that we want to show is to study one. So yeah. Okay. The problem is the addition between epoxy resins and metal is of great importance in several industry sectors. The fabrication of. Sorry. Epoxy resins and metal is of great importance in several industries.
Sorry?
Okay, so I continue, okay. So usually to fabricate good joints between copper and epoxy, we need to prepare the surface. In the case of
epoxy resins and metal is of great importance in several industries.
Okay, so we need some chemical processes. In the case of copper, we have to remove the first native oxides of organic contaminants, mainly by immersion in concentrated hydrochloric acid solution. And after that, we have to expose the surface to some oxidation agents. And in principle, sodium chloride or sodium hydroxide solutions at temperatures between 70 and 95 degrees during 3 to 5 minutes. And it creates a nucleation of acicular COO crystals on top of the CO2 layer. The problem with this junction is that they exhibit poor durability in acid environmental due to the corrosion of the oxide and the lamination problems. Also, we are focused on in the study of superconducting coils, and we want to analyze the stability of these systems that are cooled by conduction at cryogenic temperature. Here you can see the coil, is this orange part, is fixed with the epoxy. In this case was to an aluminum plate. In the case I want to show you is a copper plate, because this plate is fixed to a cryocooler, to the copper plate of a cryocooler, and then we need a very good thermal conductivity in order to remove all the heating that can be generated on the coil. This is one of the samples we have been we have been working on, it was a double pancake coil, so it's a coil with 2 layers. The coil is fixed to a copper plate, and this is fixed to the cryo cooler. And usually we use TURKUAZ 2850 FT to fix the coil with the copper plate. And in principle, we were working with aluminum. The catalyst 9 produced good effect, but when we were working with copper, we started to see some problems. Here in this curve, you can see the behavior of this coil when we apply a given current to the coil. And then when you are increasing the current, you have the typical induction voltage until you reach the critical current of the superconductor. And then you start to, the voltage start to increase. And once you reach a constant value of the current, then you have the remnant voltage that you are generating on the coil. So this experiment we have been repeating several times. You see, for instance, that after 3 times, this is the level of voltage you have on the coil. After the 4th cycle, we observe that this voltage increases. This could be due to because we have some problems on the coil that started to be degraded due to the thermal cyclings. And this is important from the superconducting point of view to have. But then when we remove the sample from the system, we observe that the coil was partially separate from the copper plate. So we fix again, we cool again, and then we recover the behavior of the coil. So it means that in this coil, the tricky point was not the degradation of the coil due to the thermal contraction when you cool down or you heat again, but the problem was that the coil was separate from the plate, so the cooling was not effective. And then that's why every time you cool down, the temperature was a little higher, and then the voltage generated by the coil was increased. So these joints were not reliable, and we decided to study a little more if we could improve these joints. Okay. So which was the problem that these joints can have to deal? So first one is that you have mechanical stresses, and then due to the thermal cycling, because you have materials with different thermal contraction coefficients. After, you have high electromagnetic Lorentz forces because you are applying large currents, electrical currents in presence of high magnetic fields. And why we select the TURKUAZ 2850 FT? Because this electric insulator, but we have alumina particles that increase the thermal conductivity of this epoxy, mainly at cryogenic temperatures. And also, this epoxy has a total linear contraction from room temperature to 77 Kelvin of 0.4%, that is slightly larger than for copper. So the idea is, if we can improve the bond strength and improve the reliability of the junction by using laser technologies to modify the copper surface micro and nanostructure. Why to use laser technologies? Because it's a clean and environmentally friendly technology. We avoid to use chemicals in the process. And also because when you modify the surface with the laser, you modify both the chemistry and the surface topography. That are the 2 key points to obtain good with joints when we make a epoxy copper joint. So The protocol that we have been using to fabricate the joints is, okay, we have been using TURKUAZ 2850. We check two catalysts, 9 and 23LV. The 9, as I told you, produce good results when we use aluminum instead of copper. But with copper, the results were not so good, as I have been showing you before. The difference between both catalysts are the viscosity and mainly the post lifetime that is longer in the case of 23LV. For this reason, in all the results I'm going to show you, finally, we have been working with this catalyst instead of 9. The copper were commercial copper plates of 99.9 purity. The residual resistance ratio is the ratio between the resistance at room temperature and 4.2 Kelvin is 100. And this purity also means that we have shown thermal conductivity. The thermal conductivity exhibits a peak around 25 Kelvin. Pure is the material, high is the residual resistance ratio value, and the thermal conductivity at low temperature. You must think that we are working in an application that works usually at temperatures around 50 to 70 Kelvin. For the laser treatment, we have been using an ytterbium pulse fiber laser with in the near infrared region and with a beam diameter of the order of 65 microns using the 1/E² criteria. And we have been working with two laser scanning configurations. The first one is the laser line scanning. In this case, the laser makes a line perpendicular to the section of the sample while the sample is moving in the perpendicular direction. So at the end, all the sample surface has been modified by the laser. Usually, we have been working with copper plates of 20 with a width of 25 microns. The line that is covered by the laser is 30 millimeters. Sorry, it was 25 millimeters. Here is 30 millimeters. In order that always this line should be higher than the width of the sample. Usually, the laser scanning speed in this line is 1 meter per second. And the sample is moved to 1 meter per hour in our cases. We have been working with pulse width of 10 nanoseconds, and we have been checking the different fluence and irradiance values from 70 millibars per centimeter square to 235 millibars per centimeter square. Also, we have been working with a bitmap configuration in which the laser makes a network of dots in top of the sample, and we can control the distance between tops, and depending on this, we can control the resolution of the line or the drawing we are making. In each position, we have applied 25 pulses, and in this case, we have been working with 120 nanoseconds per width. We have been using a irradiance value close to the lowest one in the previous case. So in order to fabricate the joints, the copper surface after cleaning were impregnated with epoxy by deep coating. Then they were cured for 24 hours at 25 degrees, applying a small pressure of 1 kilopascal. In most of the cases, the joint has been fabricated after just 5 to 15 minutes after having performed the laser treatment on the copper surface. But also we have comparison of in some cases, we have also checked what happened as a function of time. And the junctions have been fabricated 22 days after the laser treatment. Here you have the geometry of the joint that we have been using for tensile shear strength test. using the standard. Okay, and which are the results. Here you can see which are the surface topography or when we use the laser line scanning treatments. You will see that when we increase the fluence of the pulse, of the laser pulse, we increase the roughness of the surface. And you see that we have two levels of micro and a micrometer scale and a nanometer scale with different levels of macro and nanostructure. Usually the roughness is we have modified from 0.68 to 2.89 microns, and we compare with the value that we have in the non-irradiated sample. The normal roughness was 0.45 microns, and when we polish with sandpaper, we reach values of 0.2 microns. What we have seen is that the sample is very homogeneous. The microstructure is very homogeneous in all the treated area, and the color becomes darker. It seems that we have modified the oxidation of the surface. When we use the bitmap, usually what you have is holes like this. You see that the holes are surrounded by a big amount of molten material. Inside the hole, you have some spheres of molten material. And also you have an important amount of this molten material in the area that surrounds the hole. When we work with 150 and 300 dpi, the holes are separate, and you see around the holes areas that are not covered by the areas affected by the laser, while when we use 600 dpi, all the surface is affected by this kind of holes. Also, when you look to the nanostructure, you see that when we work with the laser line scanning and in the center on the hole in the bitmap, you have a very flat surface, while when you are in the area with the projected material, in the case of the bitmap configuration, you have like a fuzz nanostructure. Okay. We have been checking different properties just to know how these properties can be affected by time. And first, we have been checking, for instance, which is the oxygen content. In principle, we see that the oxygen content with time reduce in the case of the line scanning mode. That this could be due to the partial reduction of the copper oxide into more stable copper 2 oxide. In the case of the bitmap, we have the opposite behavior. Usually the oxygen content increase, and we have tried to explain this by a transformation of the copper oxide hydrophilic phase to also to a copper 2 oxide, and also to an increase. We have observed also an increase in carbon content on the surface. This is reflected in the water contact angle. So you look to the hydrophobicity, you see that the contact angle increase with time, reaching values of the order of 100 degrees, close to 100 degrees in the case of the laser line scanning mode. But also we have checked if the evolution of the contact of the epoxy contact angle, and in that case, you will see that the evolution is very similar, and it doesn't depend with time. Also, you can check the aspect of the joint. So here is we have fabricate joints between two copper plates, and after characterization, we have prepared this to see the cross section in the scanning electron microscopy, and you can see the aspect of the non-irradiate polished samples, and after the two-line scanning treatments, okay, with the lowest fluence and with the highest one. You see how the roughness increase when we increase the fluence, but even with this roughness, you see that the interaction of the epoxy with the copper is very good, and the epoxy follows all the topography on the copper. Also here you can see the oxide that the laser treatment has generated on top of the surface of the copper. Okay. One difference that we have observed is that even in all the cases we apply the same pressure, the thickness increase with the increase of the roughness of the epoxy, of the copper layer. Okay. We have also observed how was the failure of the junction, of the joint, and we have seen that when we increase in the case of the laser scanning mode, when we increase the roughness, we have a low roughness values. The failure is adhesive, and it becomes cohesive to highest one. And also we have a similar behavior when we work in the bitmap configuration with 600 dPis. In this case, when we have the cohesive behavior, it means that the mechanical properties are limited not by the adhesion of the epoxy with the copper, but to the mechanical properties of the epoxy. If we plot the shear bond strength as a function of the roughness, we see that, okay, at the beginning, when we apply low fluence value, the roughness increase very low, and all the behavior is adhesive.
Yeah.
Tamam.
Different weld
Tamam,
filler materials.
Sorry? Sorry? Yes? Okay, between 1 and 2 microns of roughness, we have some areas that are
Please continue.
Just continue, please. There is something wrong, and we are hearing you. Just please continue.
Hello? Now, can you hear? Okay. So, yeah, I'm going to just to finish, and then we have also applied we have measured the thermal properties of these joints, and then we have observed that the hello. So just to finish, I want just to say that, okay, after the adequate selection of the laser parameters, we can control the mechanical reliability of the junctions, and the mechanical properties are limited by the mechanical properties that the epoxy, rather the bonding strength. And it's important that in this case, the thermal resistance value of the joints are limited by the thickness of the epoxy layer, and in consequence, the laser technology is a good alternative to improve the adherence strength of these joints, avoiding the use of chemicals. And thank you. The laser technology is a good alternative to improve the adherence strength of these joints, avoiding the use of chemicals. And
Thank you, Professor, for a nice presentation. Now, maybe we have a question in the audience. Do you have any question? Yes, Professor. It's a good alternative to improve the adherence strength of these joints, avoiding the use of chemicals. Professor, for a nice presentation.
Dear Professor, thank you for your good presentation. I have a question. Did you hear me?
yes.
Hello?
Yes.
Did you hear me?
Yes. And you, can you hear me?
Did you hear me?
Yes.
Hello?
Yes.
Okay. Thank you for your good presentation. I have a question. Did you okay? Did you measure of electrical conductivity?
Sorry. If we are measured.
Yes.
Hocam siz sorun. Geç al.
Yes.
Okay. Thank you for your good presentation. I have a question. Did you measure of electrical conductivity?
Sorry.
Did you measure electrical conductivity of electrical resistance?
If we are measured, sorry.
Anlamadım.
Did you measure electrical conductivity of electrical resistance?
Sorry, I cannot understand which kind of measurements you are asking me.
can measure.
Sorry.
Sorry, I cannot understand which kind of measurements you are asking me.
I think there is a program, connected program. If you're here, I ask, did you measure of electrical conductivity?
If we are measure the electrical property,
Understand which kind of measurements you are asking me.
I think there is a program, connected program.
no, I mean,
Did you measure of electrical conductivity?
If we are measure the electrical property,
I mean,
Yeah, okay.
no, we
What is
cannot.
results?
no, I think
No, we have.
I mean,
Yeah, okay.
no, we
What is
can't.
results?
No, we wanted to measure the electric breakdown, but we have not measured yet.
Right, thank you, Professor Luis Alberto. Very nice presentation. Just, I want to ask the audience if you have any question, more question. I think there is no question. Thank you again, and I hope we will see you in Turkey again, maybe some other time. Bye-bye. Thank you. Thank you, Professor Luis Alberto.
Thank
Very
you.
nice presentation. Yes, I want to ask the audience if you have any question, more question. I think there is no question. Thank you again, and I hope we will see you in Turkey again in some other time. Bye-bye.
Bitti hocam, ikincisine geçebiliriz.
Right. Dear participants, we have a second invited speaker who is German Della Fuente. Her topic is laser applications in metals and alloys. Hello, Professor. Can you hear me? Are you there?
Yes, I can hear you. Can you hear me well? Can you hear me? Yes.
Durdu hocam.
Yes. Hello?
Herman, we cannot hear you.
Oh, so it's I'm supposed to have the microphone on.
Okay, we hear
Yes,
you now.
you can
Yes.
hear me now. Okay.
Yes,
So
sir.
I will share my screen. Can you hear me? Yes, I can hear you now. Yes. Shall I share my screen then? No.
Herman, we cannot hear you.
Yes. Can you hear me now? Is it okay?
I'm supposed to have the microphone on.
No, the microphone is on. Yes. Yes.
You can hear me now? Okay. So
I can hear you.
I will share my screen. Can you hear me? Yes, I can hear you now. Yes. Shall I share my screen then?
Okay. I have an echo from the YouTube transmission.
Yes, can you hear me now? Is it okay? I'm supposed to have the microphone on. No, the microphone is on. Yes, yes. You can hear me now? Okay. So I can hear you. I will share my screen. Can you hear me?
Herman, you can start. Yes.
Okay. Yes, I have a problem with the feedback from the YouTube transmission, so it rebounds what I say 1 minute before. So I try to make it straight with this, and okay, I try to go on. So I will talk. I would like to thank you for this invitation to participate in this nice international meeting. And I'm not an expert in. I'm really not an expert in welding. My expertise is in the laser material application field, and so I will give you my view of laser applications in metals and alloys. I'm a colleague of Professor Angurel, who just gave a very nice lecture, and we are talking about two different things, although they are related very much, because in both cases we are talking about modification of metal surfaces and metals in general. My lecture will be more on applications in general in metals and alloys. And this, as you see, this is a group effort. This is in our group. We work with many different things with lasers. And let me show you where I'm talking from. This is from Zaragoza. It has, you can see here a beautiful Muslim palace from the 10th, 11th century. It's called Al-Jaferia. Then we have, this is something which is more modern from the 1500s, which is a mixture of Islamic art with other cultures that we have in Spain. It's very beautiful. There are a number of towers in Aragon, in the region where Zaragoza is. This one is in Zaragoza in particular. This is a basilica next to the river in the Rio Ebro in Zaragoza. So let me tell you what I will basically talk about. I will give you an idea of what lasers are used in materials processing in general, both in the laboratory and industrial scale. Then I will talk about the laser material interaction basics. I will proceed then with laser processing of metals and alloys, basically as application examples, and I will try to give you some conclusions and outlook for the future. So basically, both industrial and laboratory lasers are used, basically are the same, the ones that are available, and they come out with emission in the ultraviolet, in the visible, in the near IR, and the mid IR range. So anywhere from 157 nanometers to 10.6 microns in wavelengths. So that's a wide variety of lasers that we can have, and these are the most common. You see, the excimer laser is a traditional laser that is used mainly in laser photolithography, and the main manufacturer of this method, which is licensed to all the manufacturers, is by Coherent, which is an American company, which now owns what was Rofin, which was a major, one of the two major German companies. It manufactures lots of different lasers. It's all over the world. Then in the visible range, you usually have now solid state lasers, which are fiber lasers, which are frequency doubled to 532 nanometers. So they emit in the green. They can be doubled to 300, sorry, they can be tripled, frequency tripled to 355 nanometers in the UV range. And later on, we can go into the near IR with diode lasers, with semiconductor lasers directly. which usually emit between 800 and 940 nanometers, to already YAG solid-state lasers, medium YAG solid-state lasers at 1064. Around 1 micron, you have also the fiber lasers and the disc laser, which are very modern lasers, which are very, I would say, very efficient from the energy point of view. And you can have lasers of this type, fiber and disc lasers, up to 20 kilowatts, which are industrially available. So I hope you can see this well. Basically, what distinguishes a laser from another optical source, energy source? Well, it's the basic properties of collimated light, which allow you to focus the laser into very narrow areas of space, of a surface, for example, versus the traditional, let's say, lamps and even sunlight. You can focus a 1 kilowatt lamp, for example, a quartz tungsten halogen lamp, which emits in a continuous mode and in a range of wavelengths, which goes from almost the UV to the near IR, with a great effort into a 3 centimeter square area. This gives you, if you calculate it for the 1 kilowatt, you have a power density of 330 watts per square centimeter from a radiance, which is the power density basically. But if you take an 8-watt laser, just only 8 watts, not 1 kilowatt, but 8 watts, and you have it irradiate at 20 hertz, that is 20 pulses per second. It's in pulse mode, 5 nanoseconds pulse duration, with a specific emission wavelength, like in this case, 1064 nanometers in the near IR, then you can get 80 megawatt pulses. You can focus it to 300 square microns very easily. And if you calculate the irradiance value for this, this is 2.6 times 10 to the 13 watts per square centimeter. You can see it's about 10 orders of magnitude higher in irradiance than this 1 kilowatt lamp. This is what makes the difference between a laser and any other energy source. So what can you do from a thermodynamic point of view, which is where most of the applications are at the moment, not all, but most? You can basically use a laser to heat, to melt, or to ablate a surface. So usually heating takes place when the laser emits in continuous mode, like a lamp or like the sun, and you concentrate it in a small spot, or you can have it in pulse mode, let's say in very long pulse duration, like milliseconds or microseconds pulses even. As you go to the pulse regime, or you can increase the intensity of the CW radiation, you can induce melting on the surface. And if you go to very high intensity levels or short pulses, then you can generate ablation, which is removing material from the surface. Of course, when you irradiate a laser into a surface, you have incident laser radiation, which can be reflected, it can be scattered, it can be transmitted, and it can generate absorption to a certain degree, enough to make this heat, to make it melt, and to cause ablation, which we will see later what it is. And so in any case, what you're usually doing is inputting heat, very localized heat into a material. Not always, but in most cases. And what is important when we talk about metals and alloys is their reflectivity to any specific laser wavelength. And so CO2 lasers were traditionally used a few decades ago, after the invention of the laser, because they were the ones available with the highest power and most developed at that time. Solid state lasers and fiber lasers were still not to a sufficient degree of development available. So you can see the CO2 laser. This is absorption going upwards. So the absorption of steel is much higher than iron, much higher than molybdenum, much higher than aluminum, or even noble metals like gold or silver. And so a CO2 laser is still being used with metals for different applications, even surface modification. but not as much as other upcoming lasers like the solid state and nowadays the diode and fiber lasers. The reason why the diode laser would be used is because for aluminum, for example, it has a much higher absorption than the fiber laser. You can see here the difference. And the fiber laser is much more absorbed by most metals than the CO2 laser. So the fiber laser has many advantages from the energetic point of view, from the quality of the output point of view, and from the absorption point of view to work with metals. And so it's one of the most common lasers used for metal work. One aspect of pulse duration, which I talked about before, just very briefly, is that if you use long pulse duration, you can usually have and expect to observe melting and a lot of heating around this area, the spot where the laser is incident. While if you go to very short pulses and on the extreme to femtosecond pulses, then heating will be a minimum, and you can get other type of phenomena and phenomena which are far away from equilibrium. We may see some of it. So you can see this is two examples. You can see here a traditional metal cutting operation with the laser. It needs very high pressure gas to assist in removing the metal. Otherwise, the metal will be self-welded and you will not get a cut. As you can see, that's a very fast cut, but when that's only by melting and gas pressure expulsion of this melt. This is a traditional cutting, but you can observe here on the right a video of a non-traditional cutting where ablation is also induced. And you can see this is 100 holes on stainless steel, about 1 millimeter thick stainless steel. You can see how fast this is the real speed. And that's the difference in the energetics when you use ablation, because ablation is related to plasma formation and shock waves, very intense shock waves. So the intense shock waves remove the metal that is being molten with this nanosecond pulse laser. We can go on to the next. Okay, this is a case of a typical case which you find in many industrial applications. And this is a very high power laser. And what I would like you to notice how the laser is reflecting into the camera. You can see this red passing through. So this has to be done in a very well sealed place, because the amount of reflection of the laser, and we're talking about kilowatts, to the surrounding is very large. And so great safety precautions have to be taken, as you can see here on this movie, which may be too loud. I hope you can hear me. I will be passing the movie through. Okay, so I would say there are three aspects you could note in this video. One is that they have a tremendous enclosure because they are working with a 20 kilowatt laser, which is extremely dangerous because especially with metals and alloys because they're highly reflecting. So it's 20 kilowatts an enclosure, and the third aspect is automation. So this system has to be completely automated, fully automated. And it's, as one of the specialists said, there's a monitoring every second of the process that is being made. And that is to ensure quality and to ensure that you're doing the right thing for this particular application, which is welding, which probably has many applications in many types of industry, and particularly in aerospace. So another application is cladding. This is used for fixing airplane engines in shops when airplanes need repairs, and it's already been in use for a long time. This is a typical application on an actual sample, and most of these applications use what we call laser beam scanning, as Professor Agurel mentioned before. And so with laser beam scanning, this is a typical procedure which is used in most laser operations, in many of them at least, where a galvanometer head is used with two mirrors which can do an XY scan over a specific area, which is defined mainly by the focusing lens. And so you can get even more than 1 by 1 meter areas, but you can usually most simple systems are around below 300 millimeters by 300 millimeters. So these typical applications for these are, for example, laser cleaning or laser decontamination. I don't know if any of these are working. I guess these are not working for some reason. So these are videos that showed how we were cleaning this. Maybe I have some later. And this is a different type of application. This is not cleaning anymore. This is structuring, surface structuring. You can see this is one type of stainless steel. You can see we can get very different colors through oxidation. This is PVD deposited titanium over a ceramic, and it's the same effect. What we're doing here is oxidizing the titanium, and the degree of oxidation or the layer of oxidation conforms the type of color that we get. You can see very distinct colors here, and also here on the steel. And this is a well-known effect. And this is what you have. This is what you can do at larger scale with microns. You can do very well ordered erase at different scales. Usually in micron scale is quite easy. And this you can generate many combinations of micron scale structuring on the surface, as you can see here, very well ordered, long range. Although these are small samples, you can see the surface finish is quite different, and there's nothing added there. It's just the surface structuring that makes change all these optical properties and other types of properties, as we will see on the metal. This is an aluminum alloy. This is on chromium, on a chromium coating, which is used in the automobile industry. And you can see here we have a diffraction grating at the surface. We have a very well ordered array. This is on the order of the visible light. So the periodicity is above 400 nanometers. So that's why we can see different colors when we change the observation angle or the illumination angle of the surface. This is a sequence that shows how we can change the on a specific surface, how we can change the structuring. And basically what I can show you here, if you initially you don't seem to see much of a nanostructure, but as you increase the power of the microscope, you can see these nanostructures. This is only 2 microns, and these nanostructures are well below the 1 micron, and they are about on the optical range of the electromagnetic spectrum. So in this case, again, around between 400 or 500 nanometers in periodicity. And you can see that as you increase the power, This is with lower power. As you increase the laser power, you change this and you change their morphology. And this is a very well-known effect. But if you do it in the right intensity of the laser and other conditions, then you can get very well-ordered array, as you see here, which maybe if you use a UV laser, they will go below the wavelength of light, of visible light, and in this case they're just above 100, 200 nanometers in periodicity. And what you can get when they're on the order of visible light is as you change the illumination and the observer's angle, you can see this is the same aluminum alloy plate. And depending on the angle, you can see all these nice colors and very intense. So this is a very nice diffraction grating. And besides that, you not only change the optical properties, but you can change other properties like the wetting properties, for example, as you see here. So this is one of those surfaces. And you can see also here on slow motion. You can see how it rebounds, and you can see underwater what the effect is. These are all stainless steel, in fact. So this is very interesting. And there is, to work in large areas, laser beam scanning is not so advantageous. So we developed what we call laser line scanning that people are using now, where we do a beam scan and we move the sample at a constant rate, so we can do any of these operations that you saw before in very large areas and at a very good control. So of course, this is also done in industry. You could call this a laser line scan, or an automated laser line scan. As you can see, this is for cleaning. Now it's not for structuring, but rather cleaning. This is on cars. So you can see there is a line which is being scanned by a robot. So you don't only have to move your sample, you can move the laser with a robot and scan a very complex volumetric, let's say, sample or any large object like this, in this case, this car, a structure, without much of a problem. So this is very advantageous, so you can use the laser in this way. Since there's not much time, I had several of these applications on stainless steel, but there's no time for that. So let me show you what the line scanning process is basically like. I don't know if this will be able to, I think this doesn't, it's a simulation, but it will show you how the laser line scanning process can be performed in large areas, so that we combine beam scanning here very fast with eventually line scanning by moving the sample at a constant rate, like it's done in many applications in industry, but this is not working, sorry. But this, we can work, for example, on these domestic applications where previously deposited thermal sprayed ceramics are then sealed and restructured and microstructure controlled by a laser line scanning, as you see here, where the original surface roughness is also reduced. And this is the result. You see this part here has been laser line scanned. This is just deposited on thermal spraying. And you can see here, this is there's still some problems with cracks. And this may be resolved by combining with heat. Let me give you, just to end, a very important laser application in metals and alloys, which is laser additive manufacturing, where selective parts of a surface of powder, metal or alloy, are molten and displaced along an axis so that a 3D object can be built, such as this, very complex 3D object, not achievable by any other method. And I don't have much time, so if anyone has any questions or wants any comment on this, I'll be very glad to do it. I would conclude saying that lasers are very useful tools for surface and materials processing. Laser technology has evolved towards the availability of wide pulse interaction regimes and very high powers, up to and more than 20 kilowatts industrially. Laser cutting and welding of metals and alloys is widely used in industrial manufacturing. Metal surfaces can be decontaminated or structured using pulse lasers in beams, scan, and line scan modes. And laser surface structure enables texture formation at the micro and nano scales, opening up new possibilities of functionalization, both optically and from many other functionalities point of view. And I would say that laser additive manufacturing is on its way to becoming a mature technique. Sorry that I have not time to discuss this more. And I would say that upcoming technologies for metals and alloys would imply using not only control atmospheres as they are already used, but also heating simultaneously. And that could open up many possibilities that are now not foreseen. And with this, I would like to thank the organizers for this wonderful invitation and all of you for your kind attention. Thank you very much.
Thank you, Professor. I just want to ask the audience, do you have any questions to ask the Professor? I think there is no. Again, thank you, sir. Thank you, very nice presentation. And again, I hope we will see you in Turkey some other time. Thank
It will
you.
be a
Bye-bye.
pleasure. And I apologize for not being there. Thank you very much to all of you. Bye.
Ademcan Uşak beyefendi. Size Ademcan Bey hakkında ben kendisi hazırlanırken ben biraz bilgi vereyim. Konuşacak konu gerçi İngilizce olarak hazırlanmış ve İngilizce de sunum yapabilir. Bizde sakıncası yok. The topic of his presentation, the impact of the laser surface tracking of titanium alloy and joining with the performance thermoplastics. Adem Bey graduated Orta Teknik Üniversitesi'nden 2019'da mezun. Malzeme ve metalurji bölümünde master yapıyor. Ve şu anda tutmada çalışıyoruz. Evet. İlgilendiği alanlar ise arkadaşlar surface range of materials, bonding technologies, thermal characterization of metals, electromagnetic characterization of low oxo metals. Neyse, Adem Bey, söz sizde. Teşekkür ederiz. Buyurun, başlayabiliriz.
Sunum aslında İngilizce hazırlamıştım yani uluslararası olduğu için. Tercih ederseniz Türkçe devam edebilirim sunumuma. Aksi takdirde İngilizce de sunabiliriz. Sizin takdirinize bırakıyorum.
Tamam. Hangisi kolayınıza gidiyorsa öyle yapın.
And I can express myself in English way because this is technical. And thank you.
Okay.
Dear ladies and gentlemen, I would like to thank you all for coming to our presentation. My name is Adem Can Uşak, and I am material test and characterization engineer in Turkish Aerospace. And I'm working on surface treatment and bonding processes. So today, I'm going to talk about the impact of laser surface treatment of titanium alloy on joining with high-performance plastic composites. As the other invited speakers have talked about some advantages of laser applications, but we will prove and some improvement or some investigation of the effects of some laser processes today. And as you can see in my outline, first of all, I will give a short introduction part, and then I will continue with our laser system, and then I will share our results, and then I will conclude and present our future studies. So let's continue with introduction parts. As you all know, Turkish Aerospace has very wide range of products. We are producing aircrafts, we are producing helicopters, unmanned air vehicle. Also, we are designing space systems, and we are also manufacturing of aerostructure of different type of aircrafts. So obviously, each project has their own requirements depending on the intended use. And as material engineering aspects, we have to define the material and considering the all requirements for each product. And as you all know, there are different type of materials are used in the aerospace industry. However, in our study, we have focused on two significant materials. The first material that we have used in our study is titanium 6 vanadium 4 aluminum alloy. This metallic alloy is playing important role in aerospace industry because it has very good and very high mechanical properties at even elevated temperature. And also they have low density and they have lower coefficient of thermal expansion when we compare to other metallic alloys. The second material that we have used in our study is polyether ketone matrix carbon reinforced composite material. And as you know, polymer matrix composites are commonly used in aerospace. And although the thermostat composite materials are used, the demand on the thermoplastic materials is increasing day by day. This is increasing because thermoplastic materials have several advantages. The most and foremost advantage is the weldability. Since you can melt the thermoplastic composites, you can easily give shape and you can easily mold this compound. And then it also increases your production rate and it enables you to have ability to recycle processes. And also thermoplastic composites have no shelf life at room temperature. So in order to combine those advantages of these similar materials, we have to join them and we have to bond them. And in order to this, before the bonding processes, we need to think about the surface treatment because we know that the bonding performance of your structure is directly related with the quality of your surface activation. In any industry, there are some conventional surface treatment processes depending on depending on your material type. If you are using thermoplastic composites, you can activate the surface with blasting processes or plasma treatment. On the other hand, if you are using a titanium alloy, you can treat the surface with chemical surface treatments like phosphate chloride treatment plus bonding primer. In our study, our aim was to investigate the new process technique and new surface processes to improve these bonding applications. So, therefore, we use NDR laser system and we optimize during this system, we optimize process parameters. In our study, we keep wavelength as 266 nanometer and we set the frequency as 10,000 hertz. However, we investigated the effect of the other process parameters like laser power, velocity of XY table, in other words, the scanning speed, and path distance, focus distance were optimized during this study. And let's start to discuss the results for titanium alloy surface. In order to investigate the effect of each parameter, we have used the contact angle measurements. If the surface of your material has lower wettability or if the wettability of your surface increases, you expect that the contact angle measurement and contact angle is needed to be decreased. Therefore, in all parameters, in all optimization progress, we investigate the contact angle measurements. And let's start with the optimization of scanning speed. When we investigate the effect of velocity or scanning speed, we need to keep other parameters as constant. Therefore, we keep other variables and parameters as constant, and we apply different velocities on the surface, and we try to obtain a minimum contact angle. During this study, for titanium alloy surface, we obtain a minimum contact angle at 35 millimeters per second. On the other hand, we also optimize the path distance of the laser system, and we observe that the minimum contact angle was obtained at 100 micrometers when we keep other parameters as constant. And then we continue. And also, we optimize the power and the focus distance during this study. And as you can see, we apply the same power at different focus distance. And we observe that, first of all, if you look at this graph on the left side, you see that if you increase the effect of power, your surface is getting more activated when you compare the contact angle results. And if you decrease, if you change the focus distance from 9x to 8x, you see the activation is increasing also by decreasing the contact angle. Therefore, when we analyze these results, we observe that we obtain the minimum contact angle at 255 milliwatts and 8x focus distance. And for now, we have discussed the results for the titanium alloy surface, and it's time to compare with some plastic composite surface. We apply the same procedure for thermoplastic composite surface, of course, and we obtain 45 millimeters per second. At 45 millimeters per second, we obtain the minimum contact angle, and it means that the wettability of your material is highest at this point. And then we also optimize the path distance, and we observed that the similar results were obtained when we applied in the titanium alloy surface. And again, 100 path distance, 100 micrometer path distance is a very good option for also thermoplastic composite surface. And this is interesting part, I think, because on the contrary of titanium alloy surface, we observed that we increase the laser power for thermoplastic composite surface, and as you can see, if you increase the laser power, your surface activation decreases and contact angle increases as well. And then, when you look at the optimizations of focus distance, we again obtain the minimum contact angle at 9x as path distance. focus distance. So finally, we have listed our optimized parameters for different types of materials, and also we investigate, we perform microscopic investigations for laser effect, and you can see in the pictures the effect of lasers. So at the end of physical measurements, we needed to apply mechanical measurement to understand the behavior of understand the bonding performance of your compound. To do this, we apply a single lecture test according to EM2243 test method, and you see the dimensions of the best specimens. And as adhesive, we use epoxy paste adhesive in the middle of the structure. And then, when we compare the results, first of all, we apply the same procedure. We apply the test into the specimens that are treated with conventional way. As I said before, for titanium alloy surfaces, chemical treatment was used, and for thermoplastic materials, fake plastic is favorable process technique, and we applied single lecture, and we obtained nearly 25 megapascal. And we also applied the test for laser treated specimens, and we obtained nearly 23 megapascal. As you can see, these results are very similar, and it's when I started to discuss for titanium alloy surface, I mentioned that when we increase the laser power, the activation is increasing also. If we increase our limitations, maybe we can reach the above the conventional treated single lecture strength value. To be concluded, laser treated titanium alloy and plastic composite structure provides higher than 20 megapascal. And also laser treatment might be an alternative process for bonding applications of titanium alloy on joining with plastic composite. Laser powered laser systems provide environmental friendly surface treatment techniques compared to conventional chemical processes for titanium alloys. Plastic and chemical surface treatments are operator dependent, and therefore achievement of repeatability and consistency is challenging. However, laser system offers lower labor costs and more consistent results for joining applications. For future studies, as I mentioned before, we have used wavelength as constant at 266 nanometer. We may change this wavelength, and we can again optimize, and we can, in the picture, we can analyze the effect of wavelength again. Also, we can investigate the SEM or SPS examination to understand the chemical change on the surface of both materials. And this is the end of my presentation. If you have any questions, I'm happy to answer.
Okay, thank you, Adem. It's a very nice presentation. Actually, if the audience doesn't mind, I just want to ask you, would you explain just a summary, 3 minutes in Turkish, then maybe we may ask correct question to you about your work.
Özür dilerim, tekrar sorumuzu cevap etmek istiyorum. Yüzey işlemlerini tekrar belirtmesiniz.
Kısaca özetlersen çalışmayı.
Tabii ki. Bizim öncelikli çalışma amacımız biraz orta kırparak anlatacağım. Havacılık sistemlerinde, malzemelerin havacılık entegrasyonunda özellikle yapışma prosesleri önemli bir boyut kazandı ve yeni malzemeler geliştikçe yeni yapışma teknolojilerine ihtiyaç doğmaya başladı. Eğer mühendisler tabii doğrusu daha farklı malzemeler kullanmak istedikçe ortaya o malzemeleri birleştirecek yeni bir proses teknolojileri gelişimine ihtiyaç duyuluyor. Çünkü yeterli şu anda hali hazırdaki prosesler bu ihtiyacı tam olarak karşılayabilmiş değil. Bizler de mühendisler olarak yeni alternatif yöntemler tasarlamaya çalışıyoruz. Şurada az önce gösterdiğim üzere farklı yüzey hazırlama yöntemleri var. Yüzey hazırlama yöntemlerinin nasıl amacı? Yüzeyinizdeki aktivasyonu artırıp yapışma performansını yukarı düzeylere çekebilmek. Hal böyle olunca tabii bazı prosesler bu konularda yeterli kalmıyor. Özellikle glassing dediğimiz kumlama prosesinde termoplastik yüzeylere istenilenden daha fazla zarar verildiği için bu prosesin yerine geçebilecek başka prosesler aranıyor. Metal malzemeler için de özellikle doğada kimyasal kullanımını azaltmak için daha farklı prosesler uygulanmak isteniyor. Ve bizler de bunu elimizdeki lazer sistemiyle farklı bir yüzey hazırlama işlemi yapabilir miyiz? Bunun hakkında bir çalışma yaptık. Bu çalışma kapsamında da farklı proses parametreleri, bu iki çok farklı malzemeyi, titanyum ve termoplastik kompoziti nasıl yapıştırabiliriz? Bu yapışma performansını nasıl karşılayabiliriz alternatif yöntemlerle? Bunlar üzerinde durduk. Bunu yaparken dalga boyunu ve lazer sisteminin frekansını sabit tutup lazerin gücünü, işte tarama hızımızı, o lazerlerin arasındaki mesafeyi, focus distance dediğimiz lazer ayarını değiştirerek belli parametreleri optimize etmeye çalışır. Ve bu kapsamda da temas açısı dediğimiz bir fiziksel test uyguladık her parametre için. Bu şu demek, bilmeyenleriniz için tekrar açıklayayım. Temas açısını şöyle buluyoruz. Yüzeye bir damla belli bir litre diyelim, belli bir litre bir damla bıraktığımızda bunun yüzeyde bıraktığı açıyı bizlere ifade eden bir test aslında, fiziksel bir test. Bunu uyguladığımızda farklı hızlarda önce optimize ettik. Hangi hızlarda minimum kontak angle'a yakalıyoruz bunu test ettik. Çünkü kontak angle'ımız düştükçe direktif ıslanabilirliğimiz artıyor ve yüzeyimiz daha aktive hale gelmiş oluyor demek. Başladık. Daha sonra yine pas distance'larımızda aynı şekilde titanyum için, titanyum alaşım için ve aynı zamanda da termoplastik kompozit için denedik. Bunlardan optimize edebildiğimiz parametreleri listeledik ve dedik ki bu parametreleri kullanarak acaba lazer sistemindeki bu uyguladığımız yapışma performansı artırılıp artırılamadığını da uyguladığımız bir mekanik testle kanıtlamaya çalıştık. Baktığımızda hem kimyasal ve glass edilmiş termoplastik yüzeylerdeki yapışma mukavemetiyle lazerle treat ettiğimiz yüzeylerin yapışma performansının hemen hemen aynı olduğunu yani. Hemen aynı demeyelim. Bunlar 1 megapascal bile tasarımda ciddi bir fark yaratabilecek düzeyde. Ya, o nedenle biz de diyoruz ki belki bu lazer sistemini daha efektif hale getirip üzerindeki kimyasal decomposition'ı ya da kimyasal değişimi de açıkça ifade edebildiğimizde ileride belki lazer sisteminde yüzey hazırlama işlemlerini alternatif bir proses olarak geliştirmeyi hedefliyoruz bizlerle. Bu çalışmanın kapsamı kısaca burada. Hepinize teşekkür ediyorum. İyi zaman ayırdığınız için.
Evet, teşekkür ederiz. Evet arkadaşlar, herhangi bir sorumuz var mı Adem?
Ben burada biraz ekleme yapabilir miyim? Kusura bakmazsanız. Adem
Buyurun.
Ayhan Kılıç'tan ben Tuşak'ta malzeme mühendisiyim. Malzeme mühendisi. Beraber çalışıyoruz arkadaşlarla. Buradaki prosesi biraz bahsettik. Adem Hocam bahsettiğini biliyor değil mi? Mikrofonu almıyor.
Nasıl tutar?
Birazcık daha belki detaylı anlatabilirsem. Şimdi tabii hava aracı yapılarında çok farklı kombinasyonlar var. Birleşiklikler var. Buradaki örneğimiz tabii termoplastik malzemeler bahsettik. Yeni bilen. Yani bu şu anda aslında hala hava aracı yapılarında sertifikasyon anlamında ciddi anlamda çalışmaların yapıldığı ve malzemelerin ve proseslerin kualifikasyon süreçlerinin devam ettiği ve uçak yapılarına entegre edildiği çalışmalar devam ediyor. Titanyumun da işte korozyon ve özellikle dış sınırı yani farklı malzemelerin bir araya gelmesinden kaynaklı olarak sağladığı avantajlardan dolayı kompozitlerle beraber bir birlikteliği var. Biz genel olarak birleştirme tekniklerinde kaynaklamadan bahsediyoruz, yapıştırma diyoruz ve işte mekanik bağlamalardan bahsediyoruz. Yapıştırmanın hava aracı yapıları için çok önemli bir şey var, anlamı var. Çünkü ağırlık kazanımı çok ciddi anlamda. Eğer biz mekanik bağlamaya ya da kaynağa yakın bir mukavemet sağlayabilirsek eğer bizim için hava aracında sağlanacak ağırlık avantajı çok çok önemli hale geliyor. Bu yüzden de aslında şu anda çok yeni bir çalışma. Bir kere onu öncelikle vurgulamak isterim. Bu tekniklerde Adem Hocam da zaten adında belirtti. Hani yeni başladığımız bir çalışmada alternatif bu proses parametre çalışmalarını geliştirebileceğimiz tüm çalışmalarla daha iyi sonuçları elde etmeye çalışıyoruz. Bu çalışma aslında şu anda yeni başladı. Adem Bey de belirtti. Biz burada daha farklı şeyleri konulara da çalışıyoruz. Çok farklı alternatif yöntemlerle çalışıyoruz. Yani bunları tekrarlı yaparak daha iyi sonuçları elde edebilmek ve bunları önümüzdeki dönemlerde de aslında sunmaya çalışmak için inşallah daha iyi sonuçları elde ettiğimizde bizim için çok önemli. Gerçekten çok önemli. Hani gördük daha önceki sunum yapan yurt dışında firmalar da var. Bu anlamda çalışmalara devam edeceğiz. Sadece bu titanyum şey değil, hani metal kompozit çalışmaları var. İşte metal çalışmaları var. Bunların hepsi aslında bu kombinasyonlar uçak yapıları üzerinde hep bizim karşılaştığımız ve bizim hem tasarım anlamında hem üretim süreçleri anlamında geliştirmemiz gereken alanlar olarak ifade etmek istiyorum. Teşekkür ederim. Bunu da ayrıca bir bilgi olarak yapmak istedim.
Evet, teşekkür ederiz. Katkılarınızdan dolayı. Sorumuz vardı. Hocam buyurun.
Teşekkür ederim sizin mekanizmanız için. Şimdi anladığım kadarıyla İstanbul'un altı bir malzeme var, üretilmesi var. Siz bunları yakıştırmak istiyorsunuz.
Tamam. Sadece.
Termoplast.
Evet.
Doğru mu? Doğru. Bunun için bir yüzey işlemi yapıyorsunuz ve uzun azap kullanıyorsunuz. Sonrasında epokside iki farklı malzemeyi, mekanik ve polimer malzemeyi yapıştırıyorsunuz. Arada kişiye strese bakıyorsunuz.
Evet.
Lazeri, NDR lazer kullandınız. Optik fokusu 8x9 kullandınız. Peki burada sonrasında kumlamayla kıyasladınız. Koronayla kıyaslamayı düşünüyor musunuz? Hani daha benzer teknikler, işte sen plastik, ilacı yüzeyi yüz temizleyecek için raf hesaplayacak. Ama burada teknoloji bazında plazma, korona, bulanıcı şarj ve benzer işte iyonize gazla elektrik alandaki şişirtmeler daha etkili olabilir diyor. İsterseniz ifade ediyorum. Sonra ben tabii yapmayacaksanız da tavsiye ediyorum. Olabilir.
Çok teşekkürler. Çok güzel bir noktaya değindiniz. Siz alternatif proses yöntemlerini ararken bunların içerisinde korona ve plazmayı çok değerlendirdik kendi aramızda. Özellikle termoplastik malzemelerin şu anda biraz hızlı şekilde bir yapışma, alternatif bir yapışma yöntemine ihtiyacı var. Bunların başında da tabii ki bahsettiğim gibi korona ve plazma geliyor. Bizler çok yakın zamanlarda plazma sisteminde bu çalışmalarda kullanmayı düşünüyoruz. Çünkü literatürde de oldukça fazla çalışma artı ve efektif yani termoplastik malzemenin üzerindeki etkisinin de oldukça iyi yönde ilerlediği gözleniyor. Bize çok yakın zamanda inşallah termoplastik malzemeler veya metal malzemeler içinde plazma teknolojisini kullanmaya başlayacağız inşallah.
İkincisi hem bir soru hem de böyle bir
Teşekkürler. Sağ olun.
bir fikir açabiliriz diye söylüyorum. Şimdi lazerle yüzey işlemi yaptıktan sonra yüzeyde ıslatma açısını ölçtünüz. Lazer gücünün artmasıyla ıslatma açısının yükseldiğini görüyoruz. Evet. Bu ne demek? Yani artık az ıslatıyor.
Evet, termoplastik malzemeler için aslında enerjiyi arttırdığımızda bunun negatif bir etkisini gördük. Evet. Bunu da şöyle bir ek not olarak paylaşayım. Termoplastik malzemeler bildiğiniz üzere eriyebilen malzemeler ve lazerin etkisini biz birazcık arttırdığımızda gözle görülecek şekilde yüzeye zarar verdiğimizi de gördük. Yani şu demek oluyor ki lazer işlemi termoplastik bir malzemeye uyguladığımızda aslında surface'daki temperature kontrolünü iyi yapabilmemiz gerekiyor. Aksi takdirde polimere ciddi anlamda zarar verebiliyoruz.
Temperature kontrolünü yani sizin ya hızla yapabilirsiniz ya da duty cycle yapabilirsiniz. Duty yani malzeme yükleyeceğiniz ısıyla alakalı bir şey. Nihayetinde lazer ısıyla yapabilirsiniz. İkincisi çalışmalarda bence şuna dikkat etmek lazım. Şimdi sizin iyi bir yüzey araştırması yapmanız lazım. Yüzeyde iki tane aktif var. Eklem yüzey mantığı var. Birincisi normal bir kumpas ölçüsünü dersiniz 5 santimetre, 5 santimetre, 25 santimetre kare bir alan. Ama bunun asıl ölçümü şudur. Bir 25 santimetre kare alanı bir roughness profil metresiyle ölçtüğünüz zaman esasında o 85-95 santimetrelere tekabül edecek. Çünkü burada mikro kraterler oluşturuyorsunuz esasında lazerle. Siz o mikro kriterleri yandan bakıldığı zaman bir testere ağzı gibi düşünün. Bu testere ağzında o üçgenlerin ne kadar yukarı çıktığı veyahut da işte konka veyahut da kepe, pik ve dip noktaların ne kadar derin ve yüksek olduğu o kadar faydalı olacaktır. Nihayetinde epoksiyle yapıştırıyorsunuz. Epoksinin de yüzey alanı ne kadar fazla olursa o kadar faydalı olacaktır. Bir yandan ıslatma açısının düşük olmasıyla ıslatılabilerek artırırken ikinci yandan raflısı bahsettiğim kriterlerle artırırsanız da bir mekanik kitlemeyle artırmak suretiyle bir optimizasyon tavsiye ediyorum. İleriki çalışmalarımızda teşekkür ederim.
Belki de onlara ek olarak da bir plazma tweet yaparsak yüzeyden aynı zamanda chemical bond'unu da sağlayabiliriz.
Plazmatik atmosferik plazmalar
Aynen.
daha ekonomik, daha ucuz, daha böyle bir geniş alanı. O da koronaya göre daha ucuz olur. Yani bilmiyorum, para problemimiz yok ama.
Burada bir ekleme daha yapıyorlar. Yani iki yönlü bakıyoruz. Hem kimyasal bir şimdi hem de mekanik bir daha buna bir ilave olarak da ben şeyi ekleyeyim. Biz burada tabii kompozit yapıda fibere zarar vermeyi istemiyoruz. Yani içine maddesiyle aslında biz deformasyon yapmaya çalışıyoruz. Çünkü esas yüklemeyi sağlayan yani mekanik kuvvetleri sağlayan yapışmada ve şeyde fiberlere herhangi bir zarar, kompozit yapıdaki fiberlere zarar vermek çalışır. O yüzden de reçine yapısının aslında bu attraction'lı lazer tarafından deforme edilmesi gerekiyor. Bu da aslında yaptığımız çalışmalardan bir tanesi.
Hocam çok güzel bir noktaya değerlendirdiniz. Zamanı biraz çalıyorum ama şunu da belirtmemde fayda var. Zaten 266 nanometrede çalışmamızın bir önemli sebebi de 266 nanometre dalga boyu matrix tarafından edilirken aslında bunun karbon fiberler tarafından da yansıtıldığı öngörüldüğü için biz bu dalga boyunda çalışma kararı almıştık. Teşekkürler.
Orada fikir analizinden biliyorsunuz.
Evet, aynen öyle.
Aynen.
Aynen.
Son olarak termoplastik endüstri belki akılsız kel toplayıp denerseniz birine göre paslanışını çıkabilirsiniz.
Evet, katkılarınızdan dolayı teşekkür ederiz. Bir güzel oldu. Konu da anlaşılmış oldu. Öğrenci arkadaşlarımız tarafından. Başka sorumuz var mı? Yani bir soru. Adem Hocam buyurun.
Evet, teşekkür ediyorum. Güzel bir çalışmaydı. Aslında söyleyeceklerim bir kısmını önceden de söyledi. Yapıştırmalarda biliyorsunuz bir gerçek alan, bir de etkili alan var. Dolayısıyla bu etkili alanın oluşmasında da ıslatma açıları oldukça önemli. Açık değil mi konu?
Düğmeye basın.
Açık. Açık. Evet. Siz sabitler arasında yapışkanın viskozitesini sabit tutmadınız veya söylemediniz. Yapışkan viskoziteleri hepsinde aynı mıydı?
Hocam doğru söylüyorsunuz.
İkincisi, geleneksel yapıştırmayla lazer karşılaştırdınız. Geleneksel yüzey hazırlamada hangisi kullanılır? Mesela termal bir yüzey hazırlamayla mekanik bir yüzey hazırlama ıslatma fonksiyonlarında çok etkili bir şey. Çünkü eğer termal bir yüzey hazırlama yapıyorsanız orada kimyasal reaksiyonlar kısmından bahsettiniz. Bir takım ıslatmayı olumsuz etkileyecek yapılar oluşturabilir. Bu açıdan da bu konularda açıklık verirseniz daha anlaşılmış olur diye teşekkür ediyorum.
Teşekkürler hocam. İkinci sorunuzdan başlayayım. Aslında konu için yani geleneksel yöntemlerden bahsettiğimizde metal malzemeler için sadece titanyum özelinde de değil, metal malzemeler için yüzey aktivasyonu kimyasal işlemlerle sağlanıyor. Titanyum özelinde baktığımızda bu kimyasal işlemler fosfat klorat dediğimiz kimyasal işleme tabi tutulduktan sonra üzerine yapıştırıcı astar eklenerek üretimde kullanılan bir teknik. Biz bunu kullandık titanyum klorat için. Termoplastik için de az önce bahsettiğimiz gibi kumlama yöntemini kullandık geleneksel yöntemler olarak ve sonuçları bunlarla karşılaştık. Diğer sorunuzda termal bir yüzeyden bahsettiniz hocam. İlk çekimimizde çok haklısınız. Termal yöntemlerde az önce bahsettiğim gibi özellikle termoplastik malzemelerde eğer ısı ve sıcaklık kontrolünü sağlayamazsak sonuçlar oldukça değişiyor. Ve yani yüzey içerisinde o 85 metrekare alanında belki de çok istenmeyen pointler oluşuyor ve bu da yapışma performansını oldukça etkiliyor. Eğer lazer sistemine baktığımızda tabii ki tüm parametreler etkili ancak termoplastik özelinde o sıcaklık kontrolünü sağlamadığımız takdirde de sonuçlarımız oldukça etkileniyor. Yani sorunuzu yanlış anlamadınız.
Teşekkür ederim.
Ben teşekkür ediyorum.
Evet, Adem'e tekrar teşekkür ediyoruz. Sertifikasını vermek üzere ben Kaynak Emek Başkanımızı buraya davet etmek istiyorum. Kendisi versin.
Hocam,
Sonra birlikte fotoğrafla çekeriz. Ben de
ben
kalsın.
de şey yaparım ama geleneksel olarak oturum başkanlarımız sunucular.
Ama eminim ki hocam sizden almayı tercih edin. Bir de adaşınız. Buyurursanız memnun oluruz.
Teşekkür ederim size. Ben de adaşım Adem Bey'e güzel sunumlar ve güzel çalışmalar.
Adem hocam, ara verilmedi. Evet, tekrar merhaba değerli katılımcılar. Kısa bir ara verdik, vermek zorunda kaldık maalesef. Bu pandemi bize bunları yaptırıyor. Şu an önümde 3 tane daha sunum var. Şu anki arkadaş online olarak katılacak. Deniz Efe. Konu başlığı Quality of the Curves for Fusion Welding of Metallic Materials. Elinde CV'si de olmayınca kendisi hakkında fazla bilgi veremeyeceğim. Fakat kendisinden ricamız başlamadan önce kısaca kendini tanıtıp bize konusunu anlatırsa memnun oluruz. Evet, şu an sizde söz Deniz Bey. Buyurun.
Merhabalar. Kolay gelsin herkese. Teşekkürler öncelikle. İsmim Deniz Efe Efer. Makine mühendisiyim. Aynı zamanda kaynak mühendisiyim, kaynak inspektörüyüm. 2012 ve 2013 yılında GSE'den mezun oldum. Yaklaşık bir 6 senedir GSE SLB-TR'de çalışıyorum. Görevlerim arasında işte firma belgelendirme üzerine auditörlük, kaynak mühendisliği derslerinde eğitmenlik ve inspektör alanı ve işte kaynak sertifikandırma hizmetleri vermekteyim. Bugün de dediğiniz gibi Quality Requirements for Fusion Welding of Metallical Materials sunumu yapacağım İngilizce olarak. Müsaadenizle başlıyorum.
Buyurun.
This is the content of my presentation. First introduction, and after second part and detailed part is requirements for instance, contract and design reviewing, organization, weld coordinator's task, etc. And later, I will finish my presentation with conclusion. Three parts you can see. Firstly, introduction. Welded manufacturing is problematic due to a heat problem, heat input distortions and welding imperfections. Therefore, quality and control systems for fusion welding has been created. Basic requirements, for example, proper traceability and storage system, welding by certificated welders, detecting proper weld parameters using WPS or VPS, choosing destructive test and non-destructive test executions and acceptable levels, experienced and knowledgeable welding coordinator, planning and recording for every control steps of calibration and maintenance. Quality systems for some of welded manufacturing could be created from normative standards, informative standards, or customer specifications or specs, such as EN 1090 or EN 15085, ISO 3834, ASME Section 9, etc. For example, ISO 3834 composes of all these standard systems. Firstly, contract and design review. The manufacturer must confirm that all contractual welding requirements and planning details of relevant quality activities are provided. For example, welding methods, non-destructive tests or destructive tests, heat treatment, personal approvals, base materials, subcontractors, test of consumables and supplying conditions, welds and locations, accessibility, sequence of welds and jigs and fixtures, WPS, WPQR control and planning, and area, planning area, for example, workshop, welding at in a workshop or work site, and acceptance criteria for weld seams must be detected before. The main purpose, reviewing company capacity about welding process, control and subcontractor, determining the deadline of project, and giving the appropriate price offer. Welding coordinator must approve the contract before sending offer. Maybe most important task of welding coordinator could be contract review before sending offer. Organizational integration of welding coordinators. The welding coordinator must be appointed independent from the production units. Control process must be managed and work log must be recorded. This is for only external welding coordinators. Tasks and areas of competence of the welding coordinator. First of all, ensuring material traceability, creating welding maps, controlling welder certificates, WPS and WPQR planning, managing before, after, and during inspections, preparing and controlling inspection and test plan, and controlling dimension reports. Subcontracting. The manufacturer must evaluate related conditions. For example, first article inspection or FAI, documentation, quality system. Manufacturer must inform the subcontractor for related works and specifications. For example, welding, non-destructive testing, welding methods, heat treatment, etc. And the subcontractor must also provide the reports and documentation for the project, quality certificate, quality procedure, etc. And also these reports must be attached at project quality file. Production and testing equipments. Machines and equipments must be listed with their capacity by manufacturer. Periodic maintenance plan must be created and traced, and maintenance records must be saved. An example of improper chassis connection, this kind of machines must not be used at production area. Welding and related activities. In a proper quality system, production planning, work instructions, weld maps, and also WPS must be prepared. Welders and operators. All welders and operators must be certificated in appreciate welding manufacturing quality system. For instance, that they could be ISO 9606-1 or -2 for operators, ISO 14732, and ASME or AVS standards. Range of certificates must ensure the related welding execution. By the way, welding certificates are timed documents. Because of this, retesting and recertificating must be performed when certificates expire. You can see two welders welding limited position. Welding procedure and qualification records, WPQR, and welding procedure specifications, WPS. WPQRs are approved documents that determine the welding capacity of the company and scope of welded manufacturing. WPS, welding procedure specification, is the welding instruction used in welded manufacturing. In a proper company or quality system, welding process must be performed according to proper WPS. WPQR process is defined with norms or standards. Some of them you can see, for example, ISO 15, 6, 10, 11, 12, 13 and 14, and ASME section 9, etc. And WPS variables are defined with norms and standards. For example, in general, in Turkey, we use ISO 15609, or also you can use ASME section 9, etc. Variables must be definitely covered by related WPQR. These variables are joint type, base material, welding wire quality, material thickness, outer diameter, weld throat thickness, weld details, heat treatment detail, current, voltage, welding speed, and heat input, and preheat and interpass temperature information must be given at the WPS. Inspection and testing. Inspection and test plan, ITP, must be made for related project to carry it out at the factory. Documentation control, for example, welding wire and base material certificates, welder certificates, WPQR, WPS, pre-production mock-up sample requirements are planned. Before, during, and after welding inspections, heat treatments controls, NDT methods, percentage, NDT personal certificates, dimension controls, final controls, and shipment controls. All of these must be planned in advance and recorded during the production. A before control, for example, improper weld preparation, about left side is a rusty material and right side is improper groove, weld groove, too much gap, you can see, and very bad angle. Also, you can see a during control, for example, measuring interpass temperature. Improper macro section, lack of penetration. These are after control. You can see excessive root penetration at left side and right side surface porosities. Again, left side, there is an improper corner turn and also lack of fusion, and right side, there is an undercut. NDT methods. Visual test. The most important NDT method is visual test, because visual test must be performed 100% for each parts, and acceptable criteria, for example, 15, 70, or 10, or 42, and acceptable criteria B, C, or D must be given. Also, the other test method and percentage must be determined according to execution standard or customer specification. They are ultrasonic test or radiographic test, UT or RT for internal imperfections, and PT and MT. They are using for surface cracks. NDT reports of rejected parts repair plans, and post-repair NDT reports must be recorded at the quality file. Inspection and test personnel must be certificated with the related standard or specification. For example, ISO, one of certificate standard is ISO 9712. NDT personnel could be level 1, 2, or 3. We have a note, minimum level 2, allowed to approve or write NDT report. This is the important part. Non-conformance and corrective actions. There must be a procedure at the company regarding non-conformities and corrective actions. Relevant non-conformities and actions must be recorded and minimize the imperfections. Repair procedures must be determined. For example, grinding methods, repair, WPS, NDT, etc. Repairs and inspection reports must be attached to the quality file of the related project. Welding consumables. Procedures involving the control of welding consumables should be prepared by manufacturer. Batch testing of consumables, CE, and other approvals, for example, TÜV or DB, test type according to EN 10204 standard must be determined, and temperature and humidity control in storage area must be done regularly. Base materials. Base materials must be stored in such a way that they are protected from external factors, for example, humidity, dirt, rust, etc. Stainless steels and non-ferrous metals should be stored in a separate area from carbon steels to prevent corrosion risk. Quality and dimensions of materials must be defined. Traceability must be ensured. Material certificates, for instance, EN 10204, 3.1 or 3.2, 2.2 must be taken during cutting process. Traceability number must be also transferred for base material and traceability. An example of color code at the storage area. And post-weld heat treatment. Heat treatment process must be compatible with welding method, base material, welding type, thickness, and construction. Heat treatment temperatures and cooling times should be defined in WPQR. Records must show that the required sequence of actions has been followed, and special heat treatment applications should be also traceable. An example, electrical resistance for welding steel, electrical resistance heat treatment method. Calibration and validation of measuring, inspection, and testing equipment. Calibration tracking system must be installed for measuring instruments. Calibration intervals must be determined. Also, reports must be kept, and also after except measuring device, also welding machines must be calibrated or verified at least once a year. For example, according to EN 50504 or ISO 17662 or any customer instruction. Identification and traceability is also important for quality systems. The traceability procedure must be defined. In this procedure, base and consumable materials traceability, color codes, barcode methods, material traceability after cutting process, welder traceability according to the relevant parts, and NDT personal traceability, marking, labeling, and code stamping must be defined. Documentation. Documents must be archived minimum 5 years. These documents also we spoke. Base and consumable material certificates, welder and operator certificates, WPS, WPQR, etc. To sum up, welded manufacturing is a special process to provide minimum quality requirements according to execution standards, norms, or customer specification because of heat input, test methods, and accessibility. Increasing the quality of welded manufacturing is possible with a quality system that complies with the above requirements and executed by experienced and knowledgeable personnel as welding coordinator or NDT personnel. Thank you for your listening. My presentation is over. Teşekkürler, sağ olun.
Thank you for your nice reading, sorry, presentation. Maybe the audience have a question, just a second. Do you have any question, please? If you have any question. Like, no. Just I was wondering, I'd like to give some words about your work. Of course, this is the welding conference, and it's welding conference. Everything is included, and especially kind of works. But when I first read the topic of this presentation, I thought it's experimental work kind of like we did before. But this is different subject, so also I have no question. Thank you, Deniz, and
Thank you.
would like to say I have your certificate and I keep it and give it to organization committee. Probably they will send it to you. Thank you and bye bye.
Thank you. Thank you for everything.
Evet, değerli arkadaşlar, bir sonraki sunuma geçeceğim. Merve Aksıoğlu yüz yüze yapacak arkadaşımız. Konuşacağı konuyu okumak istiyorum. The effect of the laser surface tracking of thermoset composite on bonding with high performance thermoplastic composite. Eğer isterseniz arkadaşlar ilgili yapabiliriz. Nasıl uygun görürseniz. Türkçe direkt yapabilirsiniz. Çünkü yabancı olmadığı için. Ya da rahat hissedecekseniz İngilizce yapıp kısaca bize Türkçe'de ama çok uzun sürmeyecek şekilde. Çünkü önümüzde birçok sunum daha var. Evet, teşekkür ediyoruz. Söz sizde. Buyurun.
Good afternoon, everybody. It's nice to be in 6th International Welding Conference and to share our studies with you, dear researchers. As Ayhan Bey mentioned, I'm Merve Aksıoğlu, a material process engineer. I'm also studying metallurgical and materials engineering master degree in metal. The purpose of this speech is to present the effect of laser surface treatment of thermoset bonding with high performance thermoplastic matrix composites. Here is the outline of this presentation. I will talk about fiber reinforced composites, additive application of aircraft composites, and the laser surface treatment. I will mention the aim of the study, laser scanning parameters, and the results. I will state conclusion, further studies, and my references. Over the past decades, composite materials consisting of a polymer matrix reinforced by carbon fibers have received considerable attention as lightweight structural materials due to their superior physical and mechanical properties. These materials also versatile because materials with different properties can be achieved by combining different types of fibers and matrix polymer in different proportions. I will mention two types of resin composites, which are innovative aerospace industrial materials, offers many advantages. First one is thermoset matrix composite, which is most commonly applied matrix in the field of continuous fiber reinforced composites in aviation industry. Lightweight structural materials are manufactured from thermoset fabrics, having high specific strength, high specific stiffness, high resistance within a large temperature range, chemical inertness, dimensional stability, and easily tailoring potential. The second composite part is thermoplastic matrix composite. Thermoplastics lends itself more easily to production automation. Parts can be made and welded by heating. Parts can be remolded, reshaped at higher temperatures. Processing scrap can be recycled. Toughness and impact resistance of thermoplastics are better than those of thermostats, which leads to superior properties of thermoplastics. Thermoplastics do not release gases or water vapor. Processing cycles are shorter because no cross-linking reaction is required like a thermostat. Thermoplastics do not need refrigeration, whereas thermostat prepregs do, and there is no shelf life for thermoplastics. Move on to adhesive application. The joining methods of each component is important for structural materials. Mechanical joining methods such as wetting, bolting are suitable for assembling metal structured components. However, composites are difficult to mechanically join due to their brittleness. The mechanical strength of composites is greatly reduced by fiber breakage and delamination from the whole machining process. Adhesive bonding is an appropriate method to assembly joining without machining process. The bonding method has several advantages, such as reduction of the secondary bond process, decreasing the weight of the structures, a uniform stress distribution, corrosion prevention, acoustic insulation. However, the main disadvantages of adhesive bonding is that bonding strength is determined by the type and the surface condition of adhesive and adherent. Moreover, polymer matrix composite exhibits low surface free energy which causes poor adhesion on surface. To achieve durable adhesion on the composite surfaces, need pre-treatment to modify surface wettability, morphology, and remove surface contaminants. NDF laser irradiation presents a new technology for surface treatment and surface modification of various adherent materials. This technology presents an alternative to use of ecologically friendly. This technology offers an alternative for ecologically unfriendly chemicals involved in conventional etching and abrasive treatments. NDF laser consists of transparent dielectric crystal. Yttrium aluminum garnet is doped with neodymium, which causes the lasering process in an active medium. First figure shows the process of medium energy level. Electron jumps from electronic energy levels of ions in the lattice medium to produce laser radiation in the near infrared spectral region. Second figure shows that it belongs to a schematic of laser surface treatment. Since the number of the projects on the use of thermoplastic matrix composite parts is increasing in Turkish aerospace, consideration of laser surface treatment for improved adhesive bonding application is required. The aim of the study is to improve adhesive bonding performance of thermoset composites with high-performance thermoplastic composites by using laser surface technology. Q-switched NDF laser system was installed in surface treatment laboratory. System has 4 different laser sources, which are 355, 532, 1064 nanometer. Surface treatment at 266 is achieved by harmonic generation from 532 nanometer source. The laser beam is diffracted from non-linear but borate crystal as 266 nanometer. The laser movement is carried by XY robots. During table movements, X and Y axis, pulse distance, and scanning speed parameters are constructed. Power and frequency is recommended to laser source. Lenses are placed in front of the laser source to be used, and a wavelength parameter is constructed. Focus distance is about lens focusing in laser head. In this study, these four parameters are optimized. I would like to explain these parameters in detail for better understanding. One of the most important effects is observed when power is changed. Laser power applied to the surface is adjusted by CIP, which is the return of actual oscillator current in percent. The power equivalents of the CIP values are given in this table. Second parameter is scanning speed that arranges laser exposure time to the surface and it adjusted by the speed of XY table movement, as I mentioned. Third one is the pulse distance that represents laser spacing between pulse lines. Final parameter is the focus distance, which is arranged from laser head level to optimize lens focus. Here is the results of this study. Physical and mechanical test results of composite thermoplastic matrix composite panels. While all setting parameters before experimental studies done on composite surface are indeed asked. First of all, thermoset matrix composites, which are manufactured from fine-finest satin fabric having 2 mm thickness, are treated by NDF laser. First study is done by keeping wavelength, frequency, scanning speed, and pulse distance parameters constant. Focus distance is adapted at different laser power. After which laser scanning, surface readability is analyzed by optic tensiometer to find optimum focus distance. Surface readability gives idea about hydrophobicity of the treated surface. When we look to contact angle versus focus distance graphic, we see a convex behavior. Low contact angle measurements are done at 9x, 10x, and 11x focus distance at each power tracks. In addition to that, highest power with CIP 57 shows most hydrophilic surface behavior among them. To find optimum focus distance at CIP 57, microscopic images of 3D surface are examined. We can see easily laser patterns with the focus close focus distance. While zooming out of the focus, laser patterns are getting invisible. Due to the increase in contact angle values before 9x and 11x, and the decrease in the macroscopic analysis of laser pattern, we choose 9x and 10x focus distance parameters to continue with mechanical tests. Thermoset matrix composites single axial test points are tested with laser and bond treated with laser and bonded with epoxy paste additive. The mechanical tests are performed for ASTM B5868 to test adhesive and surface interlocking with desired laser parameters. When we focus on single axial strength versus focus distance graphic, we dominantly see that the highest power with CIP 57 achieves highest strength at 9x focus. Therefore, optimum laser focus treatment parameters are studied for thermoset matrix composite, which are shown in this slide. We can move on to thermoplastic matrix composite laser surface treatment studies. Thermoplastic matrix composite panels, which are manufactured from PEC resin, carbon fiber bidirectional composite part, having 2 mm thickness, are treated by NDF laser. First study is done by keeping wavelength, frequency, focus distance, and power parameters constant. Scanning speed parameter is investigated at different pulse distances. As you can see, contact angle versus scanning speed graphic shows that optimum speed is obtained at blue line, which represents 100 micrometer pulse distance with 45 millimeter per second speed. We understand that low scanning speed does not provide a hydrophilic surface at each pulse distance. Some parameters may even impair the wettability of the bare surface. I would like to show three water contact angle measurements and their macroscopic analysis. First one is untreated surface, and it has 76 contact angle, and second one is blasted by glass bead particles, nearly 61-degree contact angle gained by this surface treatment. However, the macroscopic analysis shows that some silica particles are retained on the surface, despite the rinsing process. Final image belongs to laser surface treated with optimum parameters. Water contact angle is decreased from 76 to 64 degree with respect to bare surface. As surface studies are completed for two types of composites, bonding can be applied and tested. We apply application on thermosets and blasting application on thermoplastic matrix composites is done. They are the reference coupons for our study. Single lecture strength results are tabulated in this slide. When we look at mean shear strength of these configurations, we see a 23.5% improvement on the strength of single shear coupons. This improvement shows that laser surface treatment has successful effect on bonding thermosets and thermoplastic matrix composite via epoxy-based adhesive. To sum up, laser surface treatment is applied to thermosets and thermoplastic matrix surfaces to improve the adhesive bonding strength. The shear strength is increased from 13 to 16 megapascal when compared to reference configuration. By selecting adequate processing parameters, a selecting removal of the resin, surface activation, and cleaning of the surfaces are achieved. Operator dependency is eliminated and consistent and constant processes applied to high-performance composite surfaces. For the future studies, will continue to maintain surface characterization of laser-treated composite parts by SEM and XPS analysis. Other surface treatment methods, such as plasma, will be studied on composite surfaces, and laser and plasma surface treatment methods will be compared on adhesive bonding performance of these surfaces. Here's my reference are listed. And finally, thank you for your all kind attention. If you have any questions, I would like to answer. değiştirebileceğimiz parametreleri burada 4 tanesini değiştirerek çalışmamızı tamamladık. En kuvvetli değişkenimiz güç. Gücün de gördüğünüz gibi, bu tabloda gördüğünüz gibi miliwatt değerlerinde bir önceki sunumlarda bahsedilenler çok daha yüksekti mesela metal yüzeylerde ya da kesim işlemlerinde. Diğer parametremiz de tarama hızı. Tarama hızı lazer kafasının altına koyulan X ve Y yönünde giden masa sayesinde elde edilebiliyor. Bu lazer hızı da şunu etkiliyor, lazerin yüzeye maruz kaldığı zamanı değiştiriyor. Biz bu yüzden hızı da önemli bir parametre olarak görüyoruz. Fast distance'da yine lazerin gittiği, atış yaptığı atışlar arasındaki mesafe ve focus distance'da lazer head üzerinden lenslerin odağını ayarlarken yaptığımız. Sonuçlarına gelecek olursak da termosetlerde yaptığımız bu çalışmada optimum parametre olarak bunu bulmak için yine suyla temas baktık ve yine makroskopik yüzey görünümlerine baktık ve single lab shear testlerini gerçekleştirdik. Burada da bulduğumuz en uygun parametre bu şekildedir. Termoplastikte de yine buna benzer çalışmasını yaparak elde ettiğimiz optimum parametreleri ikisinin birleştiriminde kullandık. Test adızı kullanarak iki lazer taranmış yüzeyi birleştirdiğimizde elde ettiğimiz strength değeri 16.41 megapascal. Diğer referans olarak kullandığımız termosetlerde PurePly uygulaması, termoplastiklerde kullanma uygulamasıyla elde ettiğimiz single lab shear değeri 13.29. Böylece yaptığımız çalışmada %23,5 bir iyileştirme yapmış olduk. Bu yine termoplastikler üzerindeki çalışmalarını ilerleterek daha üst seviyelere çıkarılabilir. Bu şekilde biz bu çalışmada devamında yüzey karakterizasyonunu tamamlamak istiyoruz. STM ve XPS ile bakarak yüzeyin hem fiziksel olarak aktivasyonu, fiberler zarar görmüş mü, hem de kimyasal olarak yüzeydeki aktivasyonun değerini görebilmek için, hangi iyonların değiştiğini görmek için bu çalışmaları tamamlayacağız. Bir önceki konuşmada konuştuğumuz gibi plazma teknolojisiyle de bu ikisinin karşılaştırmasını yapacağız. Dinlediğiniz için teşekkür ederim.
Evet, tekrar teşekkür ederiz arkadaşımıza. Sorusu olan var mı? Konu kazanımı anlaşılığında. Benim de size sorum yok da Adem Koç hocam benim hocam bu kendisi. Hocam aklıma bir soru takıyor. Öğrenci hocasına soru sorar. Ne olursa olsun.
Ne zaman?
Yani biraz konuyla alakalı değil. Yani buradaki işte termosetler, termoplastiklerle alakalı değil de. Şimdi kaynak konferansındayız. Kaynak, birleştirme. Bunun arasında buluyor. Siz de biliyorsunuz ben seramik metal kompozit çalışıyorum. Toz metalist tekniği de bunları birleştiriyorum aslında. Yani sinterleme yapıyorum. Burada ben de kaynak yapmış olmuyor muyum? Yani tanrıların birleşmesi ya da birbirine kaynaşıp bunu biliyorsunuz katı halde oluyor, sıvı halde oluyor.
Evet.
Bu o gruba girmiyor hocam. Kaynakçı değil miyiz?
Teşekkür ederim. Aslında yemek kuyruğunu sıraya gelenler de kaynak böyle.
Öyle yapıda kaynak.
Evet, biz herkesin bir şekilde kaynaklı olduğunu söyleriz. Tabii şimdi sinterlemede de aslında bir birleşme söz konusu. Ama toz metal malzemeleri sinterlemeleri kaynaktan ziyade bonding olarak geçiyor. Yani bonding ifadesi kullanılıyor ama bir bağlanma şekli. Tabii burada bondingin sinterlemedeki biraz daha difüzyona dışında belki katı hal kaynağında onu tanımlayabiliriz.
Evet, teşekkür ederim.
Ben teşekkür ediyorum. Bir de ben Doğu illerimizden bir tanesinde çocuk okula gidiyor, ilkokula. Eve geldik de babasına diyor ki, baba öğretmen bana zor sorular soruyor. Çocuğun elinden tutar babası, gider öğretmene. Bir Hocam sen utanmaz mısın? Bu kadar samimi, bu kadar zor sorular sorarsın. Hoca diyor ki hani 2 kere 2 kaç yapar? Çocuklar babası bakmamaz görüyorsunuz yine başladı. Evet. Tabii sormak lazım. Bildiklerimizi aktarız, bilmediklerimizi de açıklıkla bilgilerimizi arayalım dersiniz. Güzel soru. Teşekkür ederim.
Ben teşekkür ederim. Merve arkadaşımızın sertifikasını ben vereyim. Evet, değerli katılımcılar, bu öğleden sonraki section'ımız bitti. Saat 5'te diğer oturum başlayacak bildiğim kadarıyla burada. Ahmet Yönetim Hocamız devam edecek. Ben katıldığınız, katkılarınız, her şey için teşekkür ediyorum tekrar. Bu oturumu kapatıyorum böylelikle. Teşekkür ederim. Ahmet Hocam'ın duyurusu olacak herhalde.
Uzun zararla bilmiyorum ama biz oturum başkanlarına da oturum başkanlığı yaparak bize destek verdikleri için bir belge veriyoruz. O belgeyle sunmak istiyorum.
Evet, oturum bitmiştir arkadaşlar. Teşekkürler.